In this video, we are going to revise some questions from Science Paper 2, Chemistry for 2021 GCE. Now here we have the first question from Section B. Laboratory safety rules and regulations are important to keep the laboratory safe. State the immediate action that a learner should take if the following happened while carrying out an experiment. Chemicals got into contact with his or her clothes or skin or mouth. So the first step that this person should take is he or she should wash the affected area with plenty water for some minutes. So we can say he or she should wash the affected area with the plenty clean water for some minutes. Okay, so this is the step that a person can take. Now we can move on to question 2. For question 2, we are looking at when he or she is bent or cut him or herself. So the first thing, if that person is bent, to cool the bent area with cool running water. Okay, or we can also say like to bandage the cut in order to stop the bleeding, or we can say to bandage the cut to stop bleeding. Okay, so maybe we can say the other importance of bandaging the affected area is also it helps to prevent the entry of unwanted infections. So that is what the person can do, or maybe we can just say reporting to the supervisor in charge of that experiment. Now let's say we have this question here. The following diagram shows a Bunsen burner, the most commonly used heating apparatus in the chemistry laboratory. So as we have seen the Bunsen burner here, then the first give one reason why the air hole should be fully open when the Bunsen burner is in use. So this hole here, why should it be fully open whenever? So the reason why we are letting this air hole to be open, we are trying to let the oxygen to enter. Oxygen is very important for the burning of a fuel or for combustion to take place. So we can say to let oxygen inside of the Bunsen burner for combustion to occur. So that is the reason why the hole should be let or should be remain open. Okay, now let's move on to question B. One of the gases used in the Bunsen burner is methane. State all the products of combustion of this gas in the Bunsen burner when the air hole is fully open. So now here, when it is fully open, we are looking at the complete combustion. So complete combustion will produce heat energy. Okay, then apart from this one, we also have water vapor and carbon dioxide. That is for complete combustion. Now, Roman number 2. Name one of the products of complete combustion of methane. One of the products of complete combustion of methane is a pollutant. Name the product and state its effect on the environment. So the name is carbon dioxide. Carbon dioxide is a pollutant. Now the effect of carbon dioxide on the environment, it causes global warming. So this is the answer. Sometimes it may cause acidic rain, though the acid formed from the carbon dioxide is a weak acid. Okay, now we move on to question 2. The question is, the figure below shows a separating technique used to separate miscible liquids. Okay, now, so before we move on, let's look at miscible liquids. So these are liquids that mix completely and forms a uniform solution. For an example, if we, let's say, get ethanol, then we mix it with water, we are going to have a solution that will form a uniform color where you can't tell where the ethanol is and water. So these two will mix completely to form a uniform solution. But if we are looking at immiscible liquids are liquids that does not mix to form a uniform solution, such as if we have cooking oil. If we have cooking oil, then you mix it with water, you are going to have a solution where the cooking oil will float on top of water. So that is not a uniform, because we'll be able to see that this is water. For example, if I have a beaker here, so if this is a miscible liquids, we are expecting here, we are expecting our water to be on the bottom. Then on top here, we are expecting to have a cooking oil. So in a case where two liquids cannot mix completely, those are known as immiscible. Now for miscible, we are looking at those that complete. For example, ethanol and water. So now here, we have been given a separating technique. So what separating technique? What is the name of this separation technique? So the separation technique that can be used to separate miscible liquids having different boiling point is known as fractional distillation. Okay, so number 2. What is the purpose of the glass beads in the fractionating column? So the glass beads, this is where they are. Now the way the glass beads are made, they are made to allow one substance to pass through, whereas preventing the other substance to pass through. What we are saying is, let's assume the mixture that we are trying to separate here is ethanol and water. So the purpose of this technique, we want to separate the two. So let's assume the ethanol is coming as a vapor. Now sometimes it may rise with some of water vapor. So now the beads here are made to allow only ethanol to pass through, but in case there is some water vapor, those water vapor must be condensed back into liquid so that it goes back into the solution. So therefore we can say the importance of glass beads to allow one substance or one liquid, one substance to allow one substance to pass through but preventing the other substance, the other substance to pass through. So that is the importance of glass beads. Okay, now we can move on to question C. The Liebig condenser kept in the slanting position as shown. So why is the Liebig condenser kept? Why is it not like horizontal position? Why is it positioned in a slanting? So the reason why it is this, to allow the distillate to flow into the collecting beaker. Okay, so the collecting beaker is this beaker here where we have the distillate. Then the distillate is the solution that is being collected. For example, if we are separating ethanol from water, we are expecting to have ethanol first because ethanol has a lower boiling point compared to that of water. So here we are expecting to have ethanol. So the ethanol that is being collected in a collecting beaker here is what we call a distillate. Now question D, apart from the mixture of miscible liquids, name two other mixtures which can be separated using this separation technique. So we like liquid air. So liquid air, if we want to separate gases such as oxygen, nitrogen, we use this separating technique. Then number two, petroleum, or we can just say crude oil. So these are the answers for question 2. Okay, now let's move on to question 3. 2.0 grams of pure magnesium ribbon reacted with exactly 100 cubic centimeters of 2.0 mole per cubic decimeter of hydrochloric acid. The first one, construct a balanced chemical equation for the reaction. So step number 1, here we are dealing with a metal. So our metal in our case is pure magnesium plus an acid. So it is a reaction between a pure metal and an acid. The product are salt plus hydrogen gas. So this is a point that you need to have in mind, that whenever you have a pure metal and an acid, you are going to have salt and the hydrogen. Now let's write our weight equation. Then from the weight equation we are going to get our chemical equation. So now the weight equation, the metal here is magnesium plus our acid here is hydrochloric acid. Now the salt is an ionic compound, and we know that an ionic compound consists of the metal and the nanometal. So whenever you are trying to name a metal, you should always begin by, whenever you are trying to name a salt, you should always begin by giving its metal, the metal name. So the metal in our case is magnesium. So we have our magnesium. Then from hydrochloric acid we get chloride always. So this is what you do. If it was the sulfuric acid, we would have gotten sulfate, then plus hydrogen gas. Okay, now let's have magnesium has a chemical symbol Mg, solid hydrochloric acid HCl aqueous. Now for magnesium is in group 2, so it has a valence of 2. Chlorine is in group 1, so it has a valence of 1. So if we interchange here, we are going to see that one magnesium atom needs 2 atoms of chlorine. So the chemical formula for magnesium chloride is this one: aqueous plus hydrogen. Hydrogen will be the atomic since it's on its own. Now from there we are going to balance our chemical equation. So begin balancing the chemical equation by first checking if our magnesium is balanced. So here we can see that we have 1, and also here we have 1. So we can see that our magnesium is balanced. Now number 2, let's check our hydrogen. From the reactant there is 1 atom of hydrogen. From the product there are 2 atoms of hydrogen. So we'll divide 1 into 2 is 2, so we need 2 in front of HCl. So you can see that we now have 2 atoms of hydrogen on the reactant and 2 atoms of hydrogen on the products. Now this 2 is also affecting the chlorine here, so you can see that even now we have 2 atoms of chlorine and also 2 atoms of chlorine. So now our equation is balanced. Now let's move on. B, we have determine the limiting reagent for a reaction. So we want to see the limiting. So the limiting reagent, it is a reactant that is used up first during the reaction. So we want to see which one was used up first before the other one was done. So now the first thing that we need to know is a reactant, a limiting reagent is always found on the reactant. So between magnesium and hydrochloric acid, we want to know which of these was used up first. So the first step that we are going to do is we are going to find the number of moles for each reactant. So let's begin by finding the number of moles of magnesium. So we can say the number of moles is equal to mass divided by molar mass. Now, as we can see, magnesium is pure. So we are not going to find a mixture for magnesium. We are just going to get its mass number. So now let's look at the question here. We can see that we have 2.0 grams of pure magnesium. So the mass is 2.0 grams over the mass number for magnesium is 24. So we can say 24 grams per mole. Now let's divide the 2 divided by 24, we can get 0.08333. So these are the moles of Mg, magnesium. Okay. Number 2, let's also find the number of moles for hydrochloric acid. Now from the hydrochloric acid, we can see that we have the volume and the concentration. So if you have the volume and the concentration and you are trying to find the number of moles, you use this formula. Number of moles is equal to concentration times volume, or volume times concentration. So let's look at our concentration is 2.0 moles per cubic decimeter multiplied by our volume is 100 cubic centimeters. Now volume should be in decimeter, so what we are going to do, we need to convert. So we say 1 decimeter cubed is equal to 1000 cubed centimeters. So our 100 cubic centimeters will be here with x, then we cross multiply. So 100 times this, we have a 1000 cubic centimeter x. Then 100 times this, we have 100 centimeter cubic decimeter cubic. So we divide by 1000 cubic centimeter, 1000 cubic centimeter, so that when we cancel, we get 0.1. So this comes 0.1 decimeter cubed. So here what we are saying is one cube decimeter has a volume of 1000 cubic centimeter. So if we are converting from decimeter cubed to centimeter cubed, you multiply by 1000, but the reverse, you divide by 1000. That is the principle behind this. So our 100 cubic centimeter in decimeter is 0.1 cubic decimeter, so that we can cancel this and this. We can now say number of moles is equal to, so 2 times 0.1, we can see that we are going to get 0.2. So 0.2 moles of HCl. Now, after finding the number of moles for each reactant, we are going to divide each reactant with its coefficient. So what we mean is, let's look at the coefficient for magnesium. So the number in front of magnesium is 1. So we are going to divide this by 1. So we can see that number of moles now is equal to 0.083. Nothing will change since we are dividing by 1. Now let's also divide by its molar ratio. So the molar ratio here is 2. So we are going to divide everything by 2. So we can see now, so 0.2 divided by 2, we get 0.1. Now after you are done dividing, let's now look at which one is a limiting reactant. So the limiting reactant will be the one with the smallest number of moles after you've divided each by its mole ratio. So you can see that 0.1 is greater than 0.08. So therefore our magnesium is a limiting. It is a limiting reactant because it has a lower molar ratio or number of moles. So 0.08 is less than 0.1. So our hydrochloric acid was in excess. Okay, so now we can move on to question C. Calculate the volume of the gas that was evolved at RTB. So the gas that was evolved was hydrogen. So now we are trying to find the volume. So now the formula for volume, if you have been given a condition, the condition is RTP. So we can say, let's just say number of moles is equal to volume over molar volume. So over 1, we cross multiply so that we can make V the subject of the formula. So we can see that we want, in order for us to find the volume, we need to have number of moles multiplied by molar volume. The molar volume here, since it's RTP, the molar volume is 24. If it was STP, it would have been 22.4. So take note of this number. So now there is a need of finding the number of moles for hydrogen. Now let's do this. So since we have the number of moles for magnesium and the number of moles for hydrochloric acid, we are going to use now a mole to mole relationship. So now whenever you are trying to find the number of moles of one substance by using the number of moles of another substance, what you do is, in a case where you're dealing with a limiting reactant, always use the number of moles of the limiting. So we can now see, let's see, magnesium is the limiting, then hydrogen is the one that we are solving for. So we can see that the mole ratio, the number in front of magnesium is 1. Then the number in front of hydrogen also is 1. So we can see that there is 1 to 1. So if there is 1 to 1 mole ratio, therefore the number of moles is equal. So since magnesium has 0.083, even our hydrogen will have 0.83 since they all consist of the same mole ratio. So now where there is number of moles, we can substitute with 0.083 times molar volume. Here the molar volume is 24. So we can now do 0.083 times 24. We can have our volume 1.992 decimeter, cubic decimeter. So these are the answers for question 3. Okay, now let's move on to question 4. Table 4 contains atomic mass units, MU, and percentage abundance for the element Q. So we can see that we have element Q, then atomic mass units. There is one with 107 and with 109. Then in terms of the abundance, 50%, and the other one with the 48. So you need to take note of, if you add the 2% here, 52 plus the 48 must give you 100%. So now, how do we calculate the relative atomic mass? So we can say relative atomic mass is equal to percentage of isotope divided by 100 multiplied by AMU plus percentage of isotope divided by 100 multiplied by AMU. Okay, so let's see what we can do. The first one, we'll look at the one with 107. So the percentage here is 52 divided by 100 times the AMU is 107 plus the one with 109, percentage is 48 over 100 times its AMU 109. Okay, so 52 divided by 100 is 0.52 times 107 plus 0.48 times 109. So we can now do the calculation. 0.52 times 107 is equal to 55.64 plus 0.48 times 109, we get 52.32. Now if we add plus 55.64, we get 107.96. So this is our answer. So this is how you should calculate the relative atomic mass by using atomic mass units and their percentage abundance. Now let's go to describe a radioisotope. So a radioisotope, first let's define an isotope: atoms with the same atomic number or atom with the same proton number but different number of nucleon number. So what we can say, these are isotopes. These are isotopes of radioactive substance with same atomic number but different number of mass number, different mass number. So this is a definition we can give for radioisotope. So you say these are isotopes of radioactive substance with the same atomic number but different mass number. So number one are here, state one use of carbon-14. So it is used in radiocarbon dating. This is a process by which scientist uses the half-life to determine how long a living organism lived on Earth and when it died. Then for iodine-131, it is used to treat goiter. So these are the answers for question 4, and that's it for this video. Thanks for watching and subscribe.